I want us to jump into more relevant material here, which is basically interactions of electrons with matter. All right. Now we are putting things into perspective. Now I think we have gotten quite a. I know there's a lot of stuff that I introduced, but I expect that some of these things have been covered at undergraduate level, and some of the things also are things that are covered at nuclear physics, which is part of what you do as part of BIPH. So far, are we together? Do you have a good background so far? All right. Okay, great. So now let's look at the electron interactions with matter. All right. So consider now you have an energetic electron traveling through matter. All right. Of course, it's going to undergo Coulombic interactions with the atoms of that absorber or the atoms of the medium in which the electrons are traversing. So they can either interact with orbital electrons, right? Or they can interact with the nucleus of the absorber atoms, all right? And so what happens is that these electrons may lose their kinetic energy through either colliding with absorber atoms or through radiative losses. What is radiative losses? Radiative loss is a loss that results from bremsstrahlung or from Coulombic interactions with the nucleus. So if an electron comes near a nucleus, it's going to experience Coulombic interactions. Of course, the electron is negatively charged. The nucleus is a net positive charge. So the electron is going to approach the nucleus, right? So the energy loss from that energetic electron would be called radiative energy loss or bremsstrahlung energy loss. All right, like I said earlier on, this would be what we call breaking radiation loss. So the electron can either collide with absorber atoms or it can interact with the nucleus. Another thing is a change of direction. All right. How does it change direction? Through radiative interactions as well. Like I said, when an electron approaches the nucleus, it's going to be redirected. So it's going to be scattered from its incident trajectory, right? Through a certain angle, which we can determine depending on the type of interaction. But let's, for now, just understand the electron can either lose energy or it can be scattered. All right, energy loss or scattering. Energy loss is described by what we call stopping power, whereas scattering is described by angular scattering power. So scattering basically is a change of direction. That's why we talk about angular. That's why there's an angular component to the scattering power, all right? So energy loss deals with the stopping power. Scattering deals with the angles, all right? Now, of course, those scattering or the collision can either be elastic or it can be inelastic. What's the difference? All right, in elastic collision, the electron is deflected, but there is no energy loss. In inelastic, there is a partial loss of energy. All right, so for elastic collision, there is deflection and no energy loss. In elastic collision, deflection plus partial energy loss. All right, and you can have an inelastic. So remember, what I'm describing here in the first 2 points is, so you can have an inelastic collision with other electrons. All right, so an electron can collide with other electrons and be deflected, but without considerable energy loss. Or it can collide with other electrons and lose part of its kinetic energy. On the other hand, it can react not with other electrons, but with the nucleus. If it reacts with the nucleus, of course, it will be redirected and deflected from Coulombic interactions and lose some of its energy through bremsstrahlung, which I said is as a result of interaction or force of attraction with the nucleus. All right. So this is what we call radiative loss. And this is just what we call scattering. The first 2 points is scattering. And that scattering can be without energy loss, which means elastic, or with energy loss, meaning inelastic. If the interaction is with the nucleus, then we get bremsstrahlung or radiative energy loss. So let's show it in the form of a diagram. So consider you have an electron E, which is traversing horizontally in this direction. And then it comes near a certain atom. All right, so the electron is traversing at a distance B away from the nucleus. All right, the distance B is what we call the impact parameter. All right, why? Is because the closer the electron is to the nucleus, the more it's going to be deflected and the more energy it's going to lose. And ultimately, the more bremsstrahlung energy is going to be released. A is simply the radius of the atom in the absorber or in the medium, right? So we are considering this scenario here, and we are going to look at different cases. So case 1 is when B is much larger than A. In other words, the electron is much further away compared to the radius of the atom. So what happens if the electron is much far away, or if B is much greater than A? It means the electron will undergo what we call a soft collision. So that means since the electron is far away, only a small amount of energy, all right, in the magnitude of a few percent, will be transferred from the electron to the orbital electron. All right. So if the electron is far away, a small fraction will be transferred. What about if the electron is closer to the atomic shell, or if it's much comparable to the radius of the atom? Well, in that case, a hard collision occurs. That means a considerable fraction of kinetic energy, up to half of the incident energy, will be transferred to orbital electrons. What about if the impact parameter B is much smaller than A? What does it mean? It means if the electron is much closer to the nucleus now. Remember, in the first case, the electron was far away, all right? So it will transfer a small amount of energy to the orbital electrons. If it's closer to the shells, it will transfer more energy to the electrons. But now, if this distance is smaller than the radius now, it means the electron is traversing here or here. It's within the proximity now of the nucleus, because now it's within the radius. Actually, it's closer than the radius to the nucleus. So in that case, since the electron is closer to the nucleus, what happens? A radiative collision occurs, which is a bremsstrahlung interaction. So what happens is the electron is going to be attracted to the nucleus and redirected and lose some of its energy in the form of bremsstrahlung. All right. The amount of energy that is lost ranges from anywhere between 0 and its incident energy. The maximum energy is normally maximum energy transfer or maximum energy loss from the electron it usually occurs for direct impact. So if the electron impacts directly into the nucleus, then we experience a maximum energy transfer. Okay, so the energy can range between 0 and the incident electron energy. So if the incident energy is 100 keV, then it means the Bremsstrahlung energy is going to be a range. So what you end up with is going to be a spectrum of energies from 0 to the maximum energy. All right. Or let me say to the incident energy of the electron. All right. I wish I could show you the spectrum here, but I can show you some other time. All right. And the peak of that spectrum will be somewhere, would be about 1/3 of the incident energy. So if the incident energy of this electron was 90 keV, all right, the spectrum of energies, if you plot a spectrum, which I say is between 0 and incident energy, it would be like a parabola, right? And the peak of that parabola would be at somewhere between 1/2 and 1/3 of the incident energy. I don't know if I'm making sense. So if you plot the energy spectrum of the photons produced, you get a range of photon energies. Why is it a range? It is a range because the photons that are produced will depend on this distance here. All right. The closer it is, the larger the energy. All right. And so the energies that you get will be a range of energies. The maximum energy you get in that among those photons produced would be the incident energy. So if you plot, your spectrum will be from 0 to E0, or to the incident energy. And that spectrum will have a peak. The peak would be 1/3 up to 1/2 of the E0. Am I making sense? Am I making sense there? All right. Okay. All right. I think I can show you. I think let me show you a figure of what I'm trying to say. There is a figure that I can show you. I believe it's here. I think on medical imaging, I covered that. If I can show you here on X-ray production. All right. So I don't know if I have another. All right. So if you plot, this is a spectrum, what, with characteristic X-rays and Bremsstrahlung. So this is a spectrum here. All right, let me use, this is filtered, so it starts from 10. Let me go to the original one, the unfiltered one. Okay, this is unfortunately filtered, but let's say it's not filtered. So if it's not filtered, it means the energy would actually start from 0 all the way to the initial or the incident energy of electrons. So it would start from 0 to 90. And the peak, which is shown by the blue line, would range from 1/3 to 1/2 of 90. So the peak here would be somewhere between 30 and 40. Right? So that's what I was trying to explain on the, if you plot a spectrum of Bremsstrahlung radiation. All right. I will share with you this part because I think it's important, but just take note that the X-ray tube here being discussed is for diagnostic imaging. It's not for radiation therapy, but the physics of how you form Bremsstrahlung is essentially the same. All right. So this is my personal notes that I created. I will share with you as well, so that you may have a fuller understanding of these things. All right. So once the electron is closer to the nucleus, now you experience radiative collisions or Bremsstrahlung emission. It is the same process used to form photons in linear accelerators that are used to treat cancer. All right. The same technique is used. They accelerate electrons, and then those electrons are bombarded to a target. And now you form these Bremsstrahlung photons that are used for treatment. If you want to do a photon treatment, so you can use the LINAC in 2 modes, either with electrons, where you simply remove the target and you bombard directly with electrons, or you put the target in the path of the electrons, and then you get photons through Bremsstrahlung and characteristic. There's also some characteristic, a small fraction, which is emitted from the transitions of electrons between orbitals. Right. And of course, I will give you questions and we will discuss, and things will make more sense. I believe problem-based learning is the best type of learning. All right. So inelastic collisions now, they can result in ionization. Like I said, you can actually bombard electrons and they can knock out other electrons. All right. So that's called ionization. So the incident electrons can eject orbital electrons, and those would be ejected. So that would be ionization, and the atom will be left with a net positive charge. Or there can be a transfer of one orbital electron from one orbit to a higher level orbit without ejection. So let's say an electron in the K or L shell, it can be excited to a higher M shell. All right, but not being completely ejected from the atom. It's simply excited to a higher atomic orbital. All right. So that's what we call excitation. All right. So these are ionizations or ejections and excitations, transition between orbitals, can result in energy losses that are characterized by collisional or ionization stopping powers. This is more of a radiation physics and dosimetry type of content. So I'm not really also going to go deep into that. I believe Dr. Joseph will teach radiation physics and dosimetry. So this is something, I'm not teaching radiation physics this year. So I'm hoping this is going to be covered there. All right. Also, in terms of the scattering, like I said, it's characterized by angular scattering power. In terms of Bremsstrahlung, you talk about radiative stopping power. All right. So I hope you understand here. So angular scattering power is for scattering. Radiative stopping power is for Bremsstrahlung. Collisional stopping power is obviously for collisions between electrons. And let's keep the Lamont relationship. It basically governs the power, all right? The power emitted in Bremsstrahlung photons, all right, which is basically proportional to the square of the acceleration of the particle, and Q, which is the charge of the incident particle, whether it's an electron with a charge of +1, of -1, a proton +1, or maybe an alpha particle with a +2. So that's basically the power emitted. All right. Linear stopping power is basically the, we can define it as the kinetic energy lost per unit path length. So that's what you call stopping power. All right. And it's given, of course, in units of energy per unit length, right? Is the kinetic energy lost per path length. So dE dx. Right? Mass stopping power, in other hand, is simply the linear stopping power divided by the density of the medium. So the linear stopping power has no relationship to the medium, right? But mass stopping power takes into account the density of the absorbing medium. So you simply have to divide the linear stopping power by the density. And of course, the units will change to mega electron volts, square centimeters per unit mass. All right. And you can characterize this total stopping power. All right. Whenever you see the density, then you know there is a mass stopping power. All right. The total stopping power would be basically the sum of collisional stopping power and the radiative stopping power. Remember, I told you that collisional stopping power results from electron interactions, right? Which is basically just ionizations and excitations. Whereas the radiative stopping power results from electrons and nucleus. Okay, so make sure you remember this, that the collisional aspect is just between electrons. The radiative aspect is between electrons and the nucleus. And of course, the total is the stopping power, is the sum of the stopping power from both components. All right. For heavy charged particles, um, for example, if we look at alpha particles, these are considered to be heavy charged particles. Neutrons are not charged particles. Electrons are not heavy. So we mostly look at things like alpha particles, and also there are other heavy particles like carbon. Carbon can be ionized as well. There are some centers, I think, in the US that focus on carbon ion therapy. All right. But those are obviously, we need special machines to achieve that. All right. So, but in that case, the total stopping power would be equivalent to the collisional. In other words, the radiative component is almost zero. There is little Bremsstrahlung for heavy charged particles. All right. And of course, we will do some tutorials on these just to put everything into perspective and see if you understand. And then for light, of course, for light particles, the total is the sum. But for heavy particles, the radiative component is almost equal to zero. I want you to basically find out why, or what's the reason why the Bremsstrahlung production for heavy charged particles is basically negligible. All right. That is something I want you to look at. Why is the radiative stopping power, or why is Bremsstrahlung basically almost negligible for heavy charged particles? That's why you see when we want to create photons, we don't use alpha particles, we use electrons, because we know they produce considerable Bremsstrahlung radiation. All right. Before I move on to photon, let me see how many slides I have on electrons, because I'm not going to cover particle range. Let me see. One thing I want to mention, let me just cover the next two slides, then I'll give you like a short break, then we'll look at photon interactions. All right. So one thing I want you to understand as well is we've already covered ionization, right? Which is just ejection of electrons and radiative collisions. But one thing I want you to remember is that the rate of energy lost for an electron beam, right? For a therapy electron beam, which means in the megavoltage energy range, for a therapy electron beam in water or water equivalent tissues like the human body, the energy lost by an electron is about 2 MeV per centimeters. This is very important. All right, remember this, that an electron loses about 2 mega electron volts for every centimeter that it travels. So as you can see, an electron loses a considerable amount of energy. That is why it does not really travel deep into tissue. So electrons are mostly used for surface level tumors like skin cancer, or superficial, at least maybe under the skin. But if you want to treat something which is like deep rooted, you're going to have to use photons. All right, those are more suited for deep-seated tumors. For electrons, due to the high stopping power or the high energy loss per unit distance, they deposit most of their energy close to the surface of the patient. So we will look at the percentage depth of curves, or PDD curves, which is basically the change of dose with depth. All right, and you see the distinct characteristics between photons and electrons in terms of how they deposit energy. All right, so electrons within a few centimeters, they deposit most of their energy within about five centimeters or so. All right, so yeah, I think that's the important part I wanted to cover. We can skip this part and this part. Yeah, we can skip these graphs. There's just one thing I want to talk about, which is the slowing down approximation, the RSDA. I'm not sure if I have it with me here. Let me just see if I have it. The continuous slowing down approximation, which is basically given by this range here, the particle range. All right. So anyway, let me just quickly talk about that, and then we'll take like a 5-minute break, and then we'll come back for about 30 minutes, and we'll stop. So the particle range basically is, remember we said the stopping power is the energy loss per unit distance, right? The mass stopping power is basically the stopping power divided by the density. So this is a mass stopping power. If you take the mass stopping power and you invert it, in other words, to power minus 1, and you integrate, you get the range. All right. Remember, a stopping power is the energy per unit distance. But if you invert, that will be the distance per unit what? Length. So the distance, sorry, I mixed up. So the stopping power is the energy per unit length. The inverse is the length per energy. It's almost like you just inverted, right? So if you invert that now, the units now are like centimeters, all right? Centimeters per unit energy. So for example, you'd say centimeters per MeV, all right? Instead of this, right? Remember, this is a stopping power, right? MeV per centimeter. So when you invert, you get centimeter per MeV. All right, so that's what I'm trying to communicate here. So once you integrate that, you get the total range. If you integrate throughout the limits of the energy from 0 to the maximum kinetic energy, then you get the total range of that charged particle. So this is the particle range, right? Is the integral of the inverse of the mass stopping power. All right. Is it clear? Please let me know if that is not understandable, and I'll try to explain in different terms. Let me know in the chat if you got that part before we take a break. So now you have the distance per unit energy. And if you integrate for all energies, then you get the total particle range R. All right, is it clear? Let me know in the chat, and then we'll take a break, and then we'll come back and do photon interactions. All right, is it clear on how we get the particle range? At least theoretically from this equation, because that's one thing I wanted to introduce to you. All right. Let me explain again. Right. So we have got the stopping power, right? I defined stopping power before, right? Stopping power, I defined it here, right? We say the stopping power is simply the energy that is lost per unit distance. All right. So energy, MeV per unit distance. So it's MeV per centimeters. That's linear stopping power. Mass stopping power, you simply take the linear stopping power and you divide by the density of the medium. Okay, so if you introduce the medium density, now you've got the mass stopping power. Remember, this is a linear stopping power. All right, this is a linear stopping power. With the density included, now is the mass stopping power. All right, you simply take the linear stopping power and you divide by the density, or times 1 over rho. Rho is the density here. All right. So if you incorporate the units of density, right, which is grams per cubic centimeters, it means your units will be like this. All right. Now, if you invert, so now remember stopping power S represents this part divided by rho. So this is S, this is S from the previous equation. Remember, say S is equal to that, right? So this part is S over P, or S over rho. All right. Now, if we put that into an equation, if we integrate, we are integrating this, but inverted now. All right. This is inverted. Where was I? I want to show you the equation. This, right? So that's the mass stopping. This is the mass stopping power. It's, of course, it's a function of the energy, all right? And you are integrating with respect to the energy, right? So what you get is a range, but the units of that range is not just going to be in centimeters. It's going to be an inverted unit of this here, of these units that I showed you earlier. All right. What I'll do is I'll give you an example of what this looks like. I'll give you an example of what this looks like, so that you can understand what I'm saying. But the units that you get will be independent now of the density. Remember, the density is already incorporated into the equation. So you will get a range, but the range that you get is not just given like in centimeters. It's going to be a range that incorporates the density. So you will have units that will be like centimeter, that will be like regardless of the density, because the density is already incorporated into the equation here. All right. So the density is already part of the mass stopping power. So you get a range, but your range will be like square centimeter per gram or something like that. All right. And you can convert into centimeters if you want by multiplying with the density. So now if I give you a specific material, you just have to multiply by the density and you get your units in centimeters. So you know, okay, so this electron travels this much distance in this particular medium. All right. For water, we know it's 2 MeV per centimeters. For water, we know this. Right? For water, it's 2 MeV per centimeter. But how about other medium? So that's why now we incorporate the density. All right. So that if I give you a specific medium, you can calculate the range in a specific medium. Whatever you get here, you just have to multiply by the actual density of that medium. Is it more clear now? In water, we know it's 2 MeV per centimeter. That's the energy loss. For every centimeter, an electron will lose 2 MeV. But how about if water is traveling in bone? All right, now we have a density dependent range. All right. Of course, you know the amount of distance that radiation travels depends on the characteristics of the medium, right? So obviously in bone, electrons won't travel as much as they do in water. They will be stopped much quicker because bone is much denser than water. So that's why we incorporate the density component. Right. And again, this is a radiation physics and dosimetry type of thing. So I don't want to like go down a rabbit hole, and I just want you to understand the basics of what stopping power is. Right. I want us to take like a 5-minute break, and then we'll start at 7:30, and then maybe we'll do 25 more minutes, and after that we'll stop. So I just want to stop here for now. Uh, have you understood what I tried to explain to you? At least in part. All right. All right. So let's meet again at let's say 7:30. Yeah, at 7:30. Okay, so let's just continue. There's two things I wanted to mention which I forgot. Um while we were speaking about electrons, right? So um the energy loss, right, from collision interactions between electrons and absorber atoms depend on the energy of that electron and also the density of the absorber. Right. So if you look at this graph here, um, this is a graph on the mass collision stopping power. All right. So the reason why the rate of collision is greater for low atomic number materials is because once the atomic number increases, the electron density decreases. Right. In other
Hi.
words, the
So you're sharing your
oh, I
screen.
forgot. Sorry. My goodness. I thought I had shared. Oh, I think I stopped sharing in the previous session, right? Oh, there we go. All right. So what I was saying here is there are two things I forgot to mention last time, which is the dependence of collision and radiation interactions on the atomic number, on the medium, and also the density. Those are the three main characteristics or features that influence the probability of which interaction is going to be more prominent. So in terms of collision interactions, um, the rate of collision energy loss, remember, if you look at this graph here on the left side, um, this is a graph of the collision stopping power versus the energy. All right. So the reason why this process is much pronounced for lower atomic number materials is because as you increase in atomic number, the number of electrons decrease per gram, what we call the electron density. Right? So the electron density decreases for high Z atoms. All right. So the rate of energy collision would be greater for those that are low Z because those have got a higher electron density or the number of electrons per unit mass. All right. When it comes to radiative stopping power, which is on the vertical axis on this slide, you will see that Bremsstrahlung depends more on the kinetic energy and the atomic number. It's actually much more dependent on the atomic number because it depends on the square of the atomic number. So the reason why you see sometimes we use tungsten as a target, this is so that we can improve the Bremsstrahlung efficiency. The higher the Z number, the better, or the higher the efficiency of Bremsstrahlung production. Okay, so the higher the kinetic energy, the better. The higher the atomic number, the better. But it's even more pronounced for atomic number because of the square component. Right? So if you double the atomic number, it means the efficiency is going to be doubled by a factor. It's going to be increased by a factor of 4. Right? So Bremsstrahlung is going to be more efficient for higher energy electrons and higher Z absorbers. So what kind of target do you want? You want a high Z target like tungsten. You want an energetic electron. So that's the reason why Bremsstrahlung is more pronounced for therapy energies that are in the megavoltage range, especially as opposed to diagnostic energies that are in the kilovoltage range. So for kilovoltage range, Bremsstrahlung is less pronounced. For megavoltage range, Bremsstrahlung is more pronounced because it's directly dependent on the kinetic energy of the incident electron. You want a high Z target because Bremsstrahlung is proportional to the square of the target atomic number. All right, so that's some of the factors you need to consider when choosing a target. All right, if you want to create photons from electrons, make sure you use a high Z target. Tungsten is one of the most popular. Obviously, for other reasons would include the fact that tungsten is a high melting point. So remember, at high megavoltage energies, especially, the target would tend to heat up. So you don't want a target that would melt at those high temperatures. So tungsten is suited because it has a high melting point. All right. So that's one of the reasons why we use tungsten, high melting point and high atomic number. All right. So that's those are the two things I wanted to mention. All right. In terms of the range, I explained to you that you're gonna get an energy which is in the units of grams per square centimeter. It's not gonna be in the normal absolute range that you are used to, which is in centimeters. All right. The range here that is given here is actually the normal range, divided by the density, because the density is already incorporated into the formula. So that's why the units come out a little bit weird. But if you multiply that result by the density of the medium, the specific medium, you would get the range in centimeters. All right. So this formula here gives you a range in grams per square centimeters.